Okay. So we're in chapter 1 and we're continuing with chapter 1. So the first thing we're doing problem number 1. We're almost all the way through. Is that enough lines? One more. All right, that should be plenty. And we're looking for ohms, kiloohms, megohms, tolerance. Okay, I think we'll do violet, yellow, black, gold. So gold gives us 5%. We'll write that down. And I look at violet. 0, 1, 2, 3, 4, 5, 6, 7. So violet's a 7. Yellow. 1, 2, 0, 1, 2, 3, 4. Yellow's a 4. And black is a 0. So that would be a 74 ohms.
Can you use that on the test?
Yeah, could you print that out? Yeah. 0.074 kiloohms. 0.00004 megohms. Now, you'd never write those two guys in blue. You'd never write it that way. You'd always write it as 47. So, all right, next guy. Blue, red, blue, red, black, gold. Okay, so gold gives us 5% again. Blue, 0, 1, 2, 3, 4, 5, 6 is a 6. Red is a 2. Is it still black? How come they put black in there again? For a 0. Okay, so that's 62 ohms, 0.062 kiloohms, 0.000062 megohms. All right, last one, and I'm done with problem number 1. White, yellow, orange. No tolerance. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's a 9. Yellow, 0, 1, 2, 3, 4. Orange, 3. So I have 3 zeros. That'd be a 9, 4 with 3 zeros. That'd be a 94 kiloohms. That'd be 0.094 megohms. All right, so now we managed to make it through problem 1. So now we'll talk about scientific notation. Scientific notation means I've got a number, I got a decimal point, I got more numbers, and then I got 10 to some other number. The important thing is scientific notation, I only have one number there. We then have engineering notation. Engineering notation means we're dealing with powers of 3s. So we could have kilo, mega. What comes after mega? No. Giga, tera, right? So that'd be 10 to the 3rd, 10 to the 6th, 10 to the 9th, 10 to the 12th. Or we could go negative and we could milli, micro, nano, pico. What comes after pico? I forget. So that'd be 10 to the minus 3, 10 to the minus 6, 10 to the minus 9th, 10 to the minus 12th. Okay, is the national debt kilodollars, megadollars, gigadollars, or teradollars? It's in teradollars, right? And for me, that's not very scary. I'm 62, I'm going to be dead, and you guys will have to handle it, right? But for you younger guys, that's a pretty scary number. Um, let's put it in some perspective here. How much money does the federal government spend every year? Anybody know? 3.5 trillion, maybe. Okay. Now I'm you, and I want to buy a house. How much is the bank going to loan me? Yeah, you personally. How much will the bank loan you to buy a house? In general, all of you will be zero. But in particular, they're going to loan you 3 times your income. And they're going to adjust that if you have a car loan or if you have credit cards, you have something else. It'll be adjusted down. But basically 3 times your income, right? So if the federal government played by the same rules that you as an individual have to pay for, then that'd be 3 times 3.5 trillion, which is 10.5 trillion. That's the problem. There's a reason the banks only loan you 3 times your income. What is it? So you can pay it back. Right. So that's the problem that the politicians need to come and come to grips with. Lenders are not happy about lending money at 4 times, 5 times, 6 times your income because they're never going to see it again. So the politicians, on the other hand, are looking at it as how we're going to pay it off with inflated dollars. You know, one lousy year of hyperinflation and it goes away. There is no national debt. I mean, one lousy year of hyperinflation and all you guys are starving, right? So it's a balancing game between the federal government and us that think that money's worth something other than the paper it's printed on. Right. But anyway, enough political stuff. Not really. Your calculator has in it the ability to, let's say, in mode, to be in normal or be in scientific or be in engineering notation. So if I put my calculator in engineering notation, I'm going to get answers like 900 times 10 to the minus 30. Or I'm going to get 37 times 10 to the 6th. Okay, and then I'm going to write that down as 900 millivolts maybe. 37 megabytes. Something like that. If I had my calculator in scientific notation, then this would be 9 times 10 to the minus 1. That would be 3.7 times 10 to the 7th. So depending on the mode that I have my calculator in, will depend on how I get my answer back. Okay. So that's just the way that is. The price of poker. Okay, well, going on to problem number 2. And it looks like I'm going to need a chart again, so, well, I already have a chart, right? I just go and get this one. Don't have to make another one. Where's copy? I got it. Got it figured out. Oh, there we go. And we'll just go to Big Eraser. Oh, that worked out. Alright, so I've got resistance, which is futile. I have voltage, I have current, and I have power. Okay, and I got I got 15K, I got 30 volts, I got 50 millivolts, 250 microamps, 80 microamps, milliamps, 80 milliamps, 40 watts, 400 kiloohms, 50 milliwatts, and that'll get us halfway done. Okay, so I have two equations I'm going to worry about. Ohm's law, which says V is equal to IR, and my power equation that says power is voltage times current. Now we can rewrite V is equal to IR using all my awesome math skills. I can rewrite this as I is equal to V over R. And I can rewrite it and say R is V over I. And then over here I could rewrite my power guy and say voltage is power over current. And I could write it as current is power over voltage. And then I could substitute the guys over here into the guys over there and say my power is I squared R, or my power is V squared over R. I could do that as well. So I could rewrite those equations in many forms. Or I can go and make a circle and something that looks like that, put a V here and an I and an R there. And then I wouldn't even have to use my 9th grade math skills. I could say voltage is current times resistance. And I could say resistance is voltage divided by current. And I could say current is voltage divided by resistance. And then I could make it bigger and do all the power stuff on it and make it completely useless. But I could do that. I could have a representation that looks like that. Okay, back to what we're doing. Is my calculator on? Yes, I have my calculator's on. I'm ready to go. And I almost have enough room. Okay, so I know voltage, I know resistance, I know the current. Current is voltage divided by resistance. So I'm going to go 30 divided by 15K. And I'm going to come up with 2 milliamps. And then I'm going to say, well, power is voltage times current. 2 times 30 is 60. 60 milliwatts. So I'm not even going to do that in my calculator. All right, now I'm going to do the next row, and I'm going to say resistance is voltage divided by current. 50 millivolts, 250 microamps. So on my calculator, I'm going to put in 50 double E minus 3 times, divided by 250 double E minus 6. Hit the enter button, and I'm going to get 200 ohms. Power is voltage times current, 50 milliamps. So I'm going to go 50 double E key minus 3, and then the times key, 250 double E minus 6, enter. And I'm going to write down an answer, and I'm going to get what? 50 double E minus 3 times 250 double E minus 6. And I get nothing because I have my stupid calculator in floating point with only 4 decimal places, and all I get is zeros. So I'm going to go to mode, and I'm going to put it in engineering notation, and then I'm going to do it again. 50 doubly. So your calculator is always going to give you the right answer, but you can still be hosed over on purpose by what mode you're in. Okay, 12.5. I knew that. 12.5 micro watts. Okay. So now I have current and I have power. Okay, so that means that voltage is power divided by current, so I'll use that. Voltage, power divided by current, 80 watts, 40 watts. 40 watts, 80 milliamps. Okay, so this is going to be a big number.
48 watts.
Is it 48 watts? All right, 48 watts. You want me to do the problem in the book? Oh, okay, if I have to. If I have to. 48 divided by 80 double E minus 3. 600 volts. Resistance is voltage divided by current. 600 volts divided by 80 milliamps. .5 k ohms. Now I am doing the thing that comes easiest, but in general, you don't. If you can help it, you don't want to use a number that you just calculated. You want to use the numbers that were given, right? So if I were doing this for real, I would not go and use 600 volts to find resistance. I would find some way to get it with the numbers that were given. But because I'm such a sleaze, I'm going to take the path of least resistance and do it with what I have and say that when I have an answer, that's good enough. Okay. So I know that power is I squared R. So current is going to be the square root of power divided by resistance. Okay, so that's what I'm going to do. I'm going to take my power. Well, actually, I'm going to put the square root in first. Square root of power, 50 double E3 minus, divided by resistance, 400 double E3. And I fat fingered my 50 and only have a 0 there, so I have to re-enter the whole thing. So square root of 50 double E minus 3 divided by 400 double E3. Oh. 353. Well, it can't be 353. We'll go with 350 microamps. Because I don't have 3 significant digits, so I couldn't keep any more than 2. Voltage is current times resistance. Okay, so I have current in my calculator already times 400 double E3 equals 140 volts. Okay, good enough? Okay, now we still have, what do we have? We have 3 more to do, right? All right, 3 more to do. And with a little bit of luck, the last thing we copied is still there. Yes, it is. Isn't that wonderful? And this is over to continued, and we have resistance, voltage, current, and power. Notice that C stands for current, C stands for coulombs, C stands for the speed of light. I mean, how are we going to put up with this, you know? Well, you should have to, so C could be a capacitor with farads, you know. Oh well, can't have everything. Well, we could have everything, we just don't. 120, 100 milliamps, 500 microvolts, 500 milliwatts, 30K, 100 watts. So I'm not writing down the answer, I'm not writing down the givens the way the book has it. I'm writing down the givens the way you should write them down. So in engineering notation, we wouldn't write 0.1K. We would write 100 watts. So why the author is hosing us over with bad notation, I don't know. But it probably because of his, we'd have to check into his parentage probably. Is probably what we need to do, yeah. Okay, so voltage is current times resistance. So this is 0.1, it moves over there, so that's going to be 12 volts. Okay, 12 volts times 100 milliamps, 1.2 watt. Now you can put those in your calculator, that'd be fine. You should get the same number. Resistance, okay. Power is V squared over R. So resistance is V squared over power. Okay, so V squared 500 double E minus 6 divided by power 0.5. 1 milliohm, 1 milliohm. That's like a short. Wow. I forgot to square the voltage. Yes, I forgot to square the voltage. Okay. Let's try it again. 500 double E minus 6 squared divided by 0.5 equals. Okay, that's much better. 500 nano-ohms. Oh, gee. You talk about a low number. Now, 500 nano-ohms, that is a short. I mean, that's like nothing. Okay, now current would be voltage divided by resistance. This is going to be pretty big, isn't it? Okay, so 500 micro divided by 500 nano. That's 1,000, right? Divided by 500 nano, and that should be 1,000, and it is 1,000. So I got 1,000 amps. Yeah, I probably do have 1,000 amps. Yeah. Not much voltage. I don't see how that voltage is going to push 1,000 amps anywhere. If I had 5 volts, so I'm standing there, I'm Steve, and I have 5 volts, and I was holding on to a wire, and the wire was 500 feet long. How many volts do I have at the other end of the 500 feet?
Depends on the wire.
None. Well, it will depend on the wire, but basically you're not going to have anything. You're going to all go away. So if I have 500 microvolts, it's not going to be able to push 1,000 amps anywhere. I mean, it's totally ridiculous. Anyway, but so am I, so that's just what it is. Now, why did this 30K get way up there out of the wrong spot? That doesn't make a lot of sense, does it? Okay, so we're back to what we're doing. I know
It's 30K,
power.
by the way.
It's 30K?
30K, yeah, not 3K.
Oh, some guys are so picky.
The roads were moving away.
Yeah. Well, I just have the wrong answer. What's the change in status? You know? Now, what are we going to use here? Power is I squared R. Okay, so current is going to be the square root of power divided by resistance. Okay, so the square root of power, 100, square root of 100 divided by resistance, 30, 1, 2, 3. Boom. 58 micro milli. 58 milli? 58 milliamps. Way to go. I put it right there in voltage and called it amps. I tell you. Alright, so now I need voltage. Voltage is current times resistance. So kilo times milli, they cancel each other out because one's 10 to the third, the other one's 10 to the minus third. I'm going to add a 0, so I have a 0 here. So I got 0, 3 times 8 is 4, 2 to carry, 3 times 5 is 15, 1740 volts. Okay. Now I'd expect you to do that in your calculator. Did you get the same answer when you did it in your calculator? Maybe? Alright. Now we're going to do problem number 3, which should be much more easier because I only have piddly little nothing to do here. So, but we'll do a edit and a paste. And we're going to do number 3. And we'll draw a line here. We have capacitance and frequency. And we have 400 hertz. Anybody ever been anywhere that uses 400 hertz?
Huh?
2,000 radians per second. Now, who did that? Who in the industrial world ever talks radians per second? This is anyway. Well, challenging. I mean, really, that's like talking out of school or something. 0.001 farads, 0.005 microfarads. How come he's got farads in a little f? 15. I've never seen that. You know, the last time I saw a little f for farads, yeah, that was like last year at this same exact time. No one uses a little f for farads. Sort of like Alan Bradley can't say normally open. Somebody went and did a patent on normally open, so now industry can't use normally open when something's obviously normally open because some idiot went and patented it. Anyway, just the way it is. That's right, 10 picofarads. All right, now, what are we supposed to find? We're supposed to find the capacitive reactance. Okay. So X sub C is 1 over 2 pi FC. So that's the calculation we're doing. Now, what is 2 pi? Anybody know? 2 pi is 360 degrees, right? So 2 pi radians would be 1 hertz, right? So if the frequency was in radians per second, we wouldn't be using 2 pi. So when I'm using frequency in radians per second, then I'd use the equation 1 over fc. Now, someone might think that that's easier, right? But no one who was here last semester would think that that's easier, would you? No. So that's what we're going to do. We're going to use 2 pi fc 1 over to do it, or 1 over fc to get the radians if I was using radians per second. Okay, so that's our plan. I'm sticking to it. Now I got to make my calculator work. Okay, so 1 divided by parentheses 2 times pi times 400 times 0.01 doubly minus 6 close parentheses equals, we'll call it 40 kilo ohms. Capacitive reactance is going to be in ohms. Okay. Did we all get the same answer? I got 39.7887, but I don't have that many significant digits, so I'm just going to round it up to 40. All right, I'm going to do it again. 1 divided by 2 times pi times 400 times 0.001. Okay, we'll call it 400 milliohms. All right. Now, 1 divided by 2 times pi times 400 times 0.005 doubly minus 6. We'll call it 80 kilo ohms. Now we should have just, it's half of this, right? Half of that one, so that would have doubled it because it's 1 over. So that would have been easy to do. We'll do the last. If this is 0.01 micro and that's 10 pico, then that's a difference of 10 to the third. So this should probably be 10 mega ohms, probably. We'll put it in my calculator and see. 1 divided by 2 times pi times 400 times 10 times 10. I hit the wrong key. Clear. 1 divided by, boom, 2 times pi times 400 times 10 doubly minus 12, close parentheses. I have 40. Why would I have 40? Oh, I'm sorry. Yes, this is 40. This has to be 42. Okay, that's fine. Okay, that's good. 1 divided by parentheses 2 times pi times 400 times 15 doubly minus 6 close parentheses. We'll call it 26. 27? No, we'll call it 26. 26 kilo? No, just 26 ohms. Okay, now we're going to do the same thing again, except now we're just going to use 1 over FC. Okay, so 1 divided by 2,000 divided by 0.01 double E minus X. Boom. 50 K. Okay, if this guy's 50K, then this guy's going to be 50 meg. If this guy's 50K, then this guy's going to be 100K. If this guy's 50K, then this guy's going to be 500 milli. Okay, so those are just direct relational type things. I don't have to necessarily put them in my calculator. But the next one I do. 1 divided by 2,000 divided by 15 double E minus X equals, and 33 1/3. So we'll call it 33 ohms. Oh good, we get to turn the page. Isn't that great? Oh, they did it to us again. Radians again. I tell you. All right, just another cross to bear. All right, so now we have inductance L, and we have frequency F, and we have 400 hertz and 2,000 radians per second, 10 millihenry, 0.5 Henry. Now, again, Henrys are normally capitalized. Why the author has chosen not to capitalize his H in Henry, I have no idea. Now, inductive reactance is 2 pi FL. And again, if I'm going to use radians per second, it would just be FL. So we'll do the FL guy first because it's easiest. And 10 milli, move the decimal point over 1, 2, 3 times 10. So this would be 20 ohms. 0.5 Henry would be half of that, would be 500 ohms. 5,000 micro. Okay, so if we move the decimal point 1, 2, 3 place, that would still be milli. So that would be 1 milli ohm. And you could probably put those in your calculator if you really wanted to. Okay, now we're going to do the top one. 2 times pi times 400 times 0.00, not 0.00, 0.01. Boom. 25 ohms. 400 times pi times 2 times 0.5. We'll call it 1.2K. 1.2K. Of course, we have to spell 0.2 correctly. That would be convenient. 2 times pi times 400 times 500 double E minus X. Boom. 1.2 ohms. Yeah, I guess that's right. All right, well, we're done with that one. Excellent. So we did 1 through 4. Now we have to do 11. Anybody look at the syllabus? Yeah, we got to do 11. Okay, so I got 11, and I got a half hour to do it in. Okay, so I want to find the voltage across A and B. Okay, and I want to find the resistor R, and I want to find the voltage V. All right, so that seems like a reasonable thing to do. I think I should just build it in Multisim and have Multisim tell me what it is. All right, so I've got 100 volts. I've got a resistor, 10 ohms, 4.5 volts. And if I go voltage divided by resistance, I know that I have 5.45 amps flowing in the circuit, and they have to be going that way. So it'd be nice to know that now, so I'll write it down. Alright. So now I come down this way and I find 25, 20. I only find 20. 20 ohms. I find that the current going this way is 1.3 amps. Well, if the current going this way is 1.3 amps and the current going that way is 5.4 amps, then the current going that way has to be 4.15 amps. And the voltage across this resistor has to be 20 ohms times that. So 2 times that would be 83 volts. So I have to have 83 volts across that resistor. Okay. Now I come this way. I find another resistor. It's what? Did I get it wrong?
No, that was answer number 8, right?
Nothing's. I have the answer to nothing yet. Nothing. Absolutely zappo. No, I haven't. No, I don't have anything. Trust me. All right, so I have 50 ohms here. Because I have 50 ohms there, and I have 1.3 amps going through it, that means I've got 50 volts, 65 volts, 65 volts through that guy. Okay, then I got this battery, and it's 150 volts. Okay. Now I come down this way and I find I've got a resistor and I got a point A and I've got a resistor and I got a point B and I don't know what it is and I'm calling it R. Okay, and then I come down this way and I see I've got 5 ohms. Now you see the current over here, this 5.45 amps? It divided up going both ways, but now it's going that way, and it's 5.45 amps. So 5.45 amps times 5 ohms means I've got 27 1/4 volts across that guy. And then I come down this way, and I find another resistor that's 15 ohms. That same current has to be flowing through them, so 5.45 times 15, I've got to have 81 3/4 volts flowing through him, and then I proceed down that way, and I have, yeah, 81 3/4 is what my calculator has. Is it not? Is it so unclear that I have to redo it? 3/4 volts. So now I've calculated everything that I could possibly get. Okay. Now I'm after this V, that R, the voltage between those two guys. Those are the things that I'm after. Okay, Kirchhoff's voltage law says if I do a path, and I'm going to pick a path that does this. If I pick that path, I'm hosed. I'm not going to pick that path. I'm going to pick a path that goes this way, like that. And I'm going to add up all the voltages on that path, and when I get done, it's going to be 0. Okay? So I'm going to start here, and I'm going to go minus 54.5. And then I'm going to come over here, and I'm going to go, because the current's going that way, I'm going to go minus 65, minus 65. I'm going to go minus 150 because my battery is going to go down. My current's still going that way, minus 27 and a quarter, minus 81 and 3/4 plus V. So I go up with that V, plus 100 has to equal 0. Now, I look at this equation, what do I see?
How'd you get minus 150 though? You had 100.
I'm right here. This is the positive side of the battery. That's the negative side of the battery. I'm going this way, so I went down.
Okay.
Yeah. All right. I see the thing that warms our heart most in mathematics, one equation, one unknown. Okay? So I'm going to go and keep the V on this side of the equation, put all the numbers on the other side of the equation. So everything that's positive will become negative, everything that's negative will become positive, and I will put down what V is. V is equal to something. So that's my plan. So I'm going to go minus 100, because that's the only positive guy, is the 100 guy. And then I'm going to go positive 54.5, positive 65, positive 150, positive 27 and 2 and 1/4, positive 81 and 3/4. Hit the equal sign. Am I really gonna get that? 278.5. 1, 2, 3, 4, 5, 6. I should have 6 things here. 1, 2, 3. 1, 2, 3. How come I can't move over and look at it? Anyway, did anybody else get the same number?
He said 8.5.
Yeah, okay. So, 1/3 of the problem solved. That is C, in case anybody was wondering. So, the answer to C is V is equal to 27.5. Okay, now I'm going to go and I'm going to look at a different loop. I'm going to look at this inner loop guy here that does this. Goes back to there. That's what I'm going to do. Okay. And I'm going to say, I'm going to start here. So I'm going to go up 150, 150. I'm going to go down 65, down 83, down. What's the voltage across that guy? 4.15 amps R. 4.15 R. Has to be 0. Again, I get to that happy conclusion. One equation, one unknown. And R is going to be, I'm going to put these guys on the other side of the equation. 65 plus 83 minus 150 divided by minus 415. Okay, so 65 plus 83. Oh, I'm not clearing this thing. What's going on? There, finally. 65 plus 83 minus 150 equals, divided by 4.15, and I get I'm going to get a half ohm. 1/2 ohm. Right, that's my answer to B. So B, R is equal to 1/2 ohm. All right, well, what's the voltage, the A answer, the voltage A to B, right, is going to be 1/2 ohm times the current, 4.15 amps flowing through it. So that'd be 2.07 volts. And that's the answer to A. And that leaves me enough time to build it in Multisim and see if I'm right. Right? Oh,
Can you go up a little bit?
yeah, sure, no problem. That good?
A lot more.
Oh. Oh, a lot more.
A whole lot.
You want to go up a, you want to go, well, you said a little.
Yeah.
Yeah, so I figured you're, a man of your word. That's what you wanted, so.
Is that divided by negative 4.15?
Yeah, but it's a negative guy on top. That when you do the math on top, you get a negative number. Yeah. So, yeah, if you came up, now, could you have negative resistance there? Yeah. Did I do it wrong?
B equals 278.5, and then you throw it down, B equals 27.5.
Are you trying to tell me there's something wrong?
I'm asking you to do something wrong.
I would imagine that this should be probably 8, yeah. In fact, I don't even think it should be that. I think it should probably be 280, because I doubt if you have more than 2 significant. Well, you're given 3 significant digits though in the 1 voltage you're given. But even so, I can't imagine having 4 significant digits or even
Well, that makes a
3.
little bit more sense.
Yeah, so 280 is better? Yeah. So now the issue is, do we build it in Multisim and just show how brilliant the instructor is? Or to catch it because it's wrong? Or do we go to lunch early?
We go to lunch.
So we're going to go to lunch early? Okay, you're going to trust me? Now, on the chapter 1 through 3 test, there will be a problem 1, 2, 3, 4, and 11. Okay, so each of those things will be on the first chapter test we do. Yeah. Now they'll be truncated, right? Except number 11 will have 3 times the components on it, right? Well, probably not.